Greetings all, and thanks for joining our Warkwyn webinar today. My name is Kent Peterson, and I am happy to present to you an hour session introducing you to Microflown technologies. Incorporated in the beautiful Netherlands in 1998, and after the invention of the unique Microflown particle velocity sensor, Microflown now has an incredible set of tools which allow the user the ability to visualize particle velocity and vectors while simultaneously measuring sound pressure levels. Today we'll be stepping through that product line with Jeroen Verbeek, Microflown Sales and Marketing Manager. We'll look at how the Microflown sensor measures particle velocity, the digital acquisition tools, visualization tools, and then take some time to look at some interesting case studies. Again, thanks for joining us. We appreciate your time and hope that you enjoy the session and gain some great insight on how Microflown can increase your measurement accuracy while saving tons of time locating your noise or vibration problems. At this time, I'd like to turn it over to my friend Jeroen. Hello, Jeroen. Take it away.
Good morning, Kent. Yes, welcome to our webinar today about particle velocity sensors and solutions. So Ken already gave a quick introduction. So I think this is the best slide, of course, of today. Those two handsome gentlemen over here. So you're all familiar with Kent. I will also quickly introduce myself. My name is Jeroen Verbeek. I'm, as Kent mentioned, working as sales manager for the NBA unit at Microflown Technologies. And actually, I'm already considered here part of the inventory of the furniture. So I'm working already over 14 years in Microflown. As Kent pointed out, there's like a Q&A section in the Zoho here. Yeah, I think if you click it, it will open. You can address questions here that we can address in the chat or later in the question and answer time frame at the end of the webinar. If you have something that you don't want to address to all the audience, please start with private. Then we will solely reply to you. And as mentioned, we'll address most of the questions later on at the end of the webinar. So, quick outlook for today's webinar. What content will we share during approximately the next 45 minutes to max 1 hour? Very brief introduction to the company. Moving forward to the core of the company, the introduction of the particle velocity sensors. Talk a bit about the sensor and solutions that we offer, and end up with a Q&A session. So let's get rocking and start with a very brief company introduction. So I'm sitting somewhere. Let's see if I can move the mouse onto it. I think I'm sitting somewhere here at this moment. So this is where Microflown is located in the beautiful city of Arnhem in the Netherlands. So particle velocity sensors was a bit of the motivation, like the trigger of what we're going to talk about. So sound pressure is something that we are all very familiar with, and actually sound pressure is something that humans are susceptible to. We humans can hear sound pressure, and for more than 100 years or even longer, we developed tools based on sound pressure to help us better understand sound, quantify, localize, etc. So here you see a nice picture of two German who look like Mickey Mouse with some two big ears to get better direction of the sound. And 1 second to move the mouse. So naturally, over all those years, the technology evolved and improved a lot. And still, there is some practical limitations that can occur based on microphone-based solutions. So, for example, reverberation can play a big role in biased results. If you look at really low frequencies where you have very long wavelength, if you're using like a scalar value that has no information about direction, can make it difficult. You have like to use a spatial distribution of sensors in like an array of microphones. You limit the operational frequency by that. So already since some time, it started back in 1994 with a new approach based on particle velocity sensors to complement the sound pressure, but moreover also offer a new perspective and enable new possibilities to measure and visualize sound. And this is still ongoing. So as we could see, the company started back in 1994, where the sensor was invented at the university, the Technical University of Twente, which has like a special faculty for including like a clean room technology for MEMS sensors. Company was founded a few years later in 1998 as Microflown Technologies, and we're running now the company just over 20 years, and there's a lot of big landmarks that have been going on along the way. As mentioned before, we are like headquartered here in Arnhem, the Netherlands, but we have like a strong network of value-added resellers and distributors all over the globe. And we see one nice blue dot over there as well. Here, that's where Warkwyn is located, which are one of our partners for the US market. Besides looking at it from a geographical perspective, what markets does Microflown serve? We are very strongly serving the automotive market and the affiliated companies in like ground vehicles. Increasing need for our solutions and growing market in other segments like appliances and electronics, heavy industry and machinery, aerospace, aviation. Another segment that we are aiming for is not as much R&D focus as we typically do, but like end-of-line quality control. So using the acoustic signature to classify if a product is produced good or bad. So ensuring that no faulty products are delivered to the end user. Also some building acoustics, environmental noise, and also we work with educational research institutes. So we have a lot of cooperations in the market, also with established university. So for example, like in the US with Rensselaer or Penn State. So as we can say, we proudly work with the best. So just some references here. I'll not go into deep. You can look at it yourself as well, but many familiar blue chip companies in different market segments. So let's move on to the next chapter, particle velocity sensors, or so-called Microflown sensor, the core business of our company, the thing that makes us unique and differentiate us from other companies. So we're going to look a bit more in the fundamental things behind it, how it works, what is the benefit, and how we can use it. So what we always start up with is like some nice animations to tell a story. So if this is a sending wave tube. So on one side we see like the speaker creating a wavefront, and what we can see here is like sound pressure is a force. it is scalar. So what happens is that particles get compressed together by the experience of a force. And like maybe some of you experienced as well, not everybody likes their neighbors. Same applies here. So the particles don't like their neighbors, and they're waiting for it. So what you can see, the particles are compressing together, and they imply increasing the force. So that's what you can see here, like particles compress, and you create like the wave pulse. So what we have as the wave pulse passes through, the particles in the air oscillate back and forth about the equilibrium positions. But it's like the disturbance which travels. It's not the individual particles in the medium. And you can see on the slide, like we highlighted some individual particles by a red dot. You can see they're moving back and forth and go back to the original position, whilst we see the wave traveling. And actually, this makes kind of sense. So I was it last year? No, the year before, I was visiting Warkwyn in the US, and we went like to a nice baseball match of the Minnesota Twins. At that time, they didn't do the wave, but sometimes what you see in a sports stadium is that people do the wave. So what you have is very similar here. So in the end, when we have the wave in the stadium, what you see is like the wave moving through the stadium, but like the people in the stadium don't actually move, but they just jump up and go back to the original position. So this is like very similar to what is happening here with the sound, where we have the sound pressure wave and where we have like the local oscillation of the particles in the air. So just to make like a analogy to other quantities in physics, what we have here in acoustics, the complete sound field can be classified by the two quantities of sound pressure, particle velocity. So as mentioned, the PVL is a force, a scalar factor, so it can tell you very much how much the sound is. That's what we typically use also for environmental measurements with regulations. We have like a sound level meter to measure, okay, this is the limit. Do we measure the limit, yes or no? The particle velocity, on the other hand, can be is a quantitative value, but it also adds a direction to it. So that's like the unique thing. And that's like very similar if you look at energy to potential kinetic energy, or in voltage, electricity field to voltage and current. So we create microphone sensors based on that, and we're going to talk about a few things: the working principle, and like why it's beneficial to mention. That's related to the directivity and the near field effect. So let's start with the Microflown sensor. So this is like completely different than the type of sensor that we're used to. So typically, if you look at a sound pressure microphone, what we look at is like a moving membrane. But what we use here is a MEMS technology. So MEMS stands for microelectrical mechanical sensor. And this MEMS sensor we can use to capture directly the acoustic particle velocity. So what happens when the wavefront comes to the first wire? There will be a heat interchange. So these two platinum wires that we use in the MEMS sensor, you can see them here on the picture. They're about 100 times, 200 times thinner than a a human hair, so it's really small technology. They are heated up by current to approximately 200 degrees Celsius. And what we are using is like a temperature differential sensor. So what I was mentioning, what happens is like, yes, now it animates. When the wavefront comes to the first wire, there will be a heat interchange. So what will happen is like basically two things. The particles will warm up, but also the first wire will cool down. Then as the wavefront will continue propagating through the medium, it will reach the second wire, and the second wire will cool down less due to the fact that the particles have been heated up by the first wire. So what happens is that the difference in temperature of the wires cause like a different electronic resistance. You can see on one side there's like the input, there's like a coupled circuit. On the other side, we see a decoupled circuit. So the same comes in from one side, but due to the change in resistance caused by the temperature, there will be a different voltage coming out of the two wires on the other side. So this is how we can measure with this unique technology the acoustic particle velocity. So there's some significant difference between pressure and particle velocity. So we're going to talk a bit about that and why it is interesting to use particle velocity as alternative for sound pressure. So I already quickly mentioned the two things, the directivity and the near field effect. So we start with the near field effect, and that's like related when you measure with the sensor relatively close to the source or like the structure of interest that you want to measure. So particle velocities close to a source perceive a higher signal than sound pressure. So if we look at the animation, we put like a pressure velocity probe in the far field. What you see there is like they will be equal in amplitude and phase. But if we move with pressure and velocity close to a vibrating surface, what we can see is that sound pressure increases linear, whereas the particle velocity increases exponential. So we see here now, we go close to pressure velocity to the source. Pressure increases, but velocity signal increases much more. So this is related to the effervescent energy that we have in the near field. So one thing is, if we measure close to the source, we have with velocity compared to pressure a really high level that we can measure. On the other hand, the second part of the near field effect is related if there's like external sources. So not like the source that you want to measure, but there's like surrounding noises of the environment, background noise and reflection. So what you have, if you have a rigid surface, and what you have is a sound wave that is reflecting on the surface. What you can see, the reflecting sound wave on the surface of pressure is in phase with the incoming sound wave. So the cool thing about particle velocity, it is a vector quantity. So as you can see here, it has like a plus and a minus. So if sound is coming from one side compared to the other side, it's 180 degrees out of phase. So what we get with particle velocity, if it reflects, you can see if we consider a complete rigid surface as full reflection, that it gets the same amplitude, but it's 180 degrees phase shifted. So if you look at the total contribution of the reflection, with pressure, you actually get amplification. So an increased effect of the surrounding noise sources. But due to the fact that with particle velocity, the incoming sound wave and reflecting sound wave are 180 degrees out of phase, you get like a so-called like natural cancellation of the surrounding noise. Then the last part is like related to the directivity that you have with particle velocity sensors. As I mentioned, the sound pressure is scalar. It measures sound in all directions. So it's very similar to our ears. We have two ears to get better understanding of the direction of sound, where sounds are coming from. But in the end, we're sensitive to sound in all directions. But with particle velocity, we have a so-called figure-of-8 polar pattern. And so it's sensitive to sound in one direction. If sound comes more under an angle, it will be less sensitive to pick up the sound. And if sound comes from this side, it will be not susceptible and sensitive to it. Then it gains back sensitivity, and it will be sensitive from this side. However, as we mentioned, there's like a 180 degrees phase differential from sound coming from this direction or from the other direction. And a really cool feature here as well is that it's preserved for the full frequency range. So it's not limited in frequency. So it works for both low and high frequencies. And this directivity, this kind of spatial filtering, like works like in the full range and can have like a big impact also in reducing unwanted sources. You can also imagine that like the more closer you go to the source, the more you can benefit and like separate sources. So if you measure at a distance, if you have two close sources, you get like, due to the spatial aliasing, you will get like one source. But if you go really close, due to this effect, you can separate even sources that are really close to each other. So here we're just highlighting this effect. Unfortunately, there's no audio. So what we do here is we measure sound with a pressure and velocity probe, in this case at the HVAC unit. And if you look at the spectral analysis, you can see that you will get much more dynamic signal-to-noise ratio with the particle velocity sensor. So if we look here, you just see like a small peak in the spectra, 20 dB with pressure. But when we measure the same point with particle velocity, you have over 40 dB dynamic range. When we talk about the directivity, what we mentioned, the figure-of-8, if we rotate the probe with sound pressure, maybe I will just see if I can, in the video, shortly pause it. You can see if we rotate the probe with the with the sound pressure level, it overall stays almost the same. You'll see hardly any change. Boom. Yeah, no, here we get spectral analysis. You see there's hardly any change. So, sorry. Why it moves automatically. Yeah, you can see hardly changes. And when we do the same with particle velocity, you can see a significant increase of over 20 dB when we rotate the sensor from the non-sensitive to the sensitive direction. So this video is available on our website or LinkedIn, so you can play it back with sound and experience yourself the power of the particle velocity. So how it can give you advantages compared to the sound pressure. So to sum up, if we fully exploit the make advantage of the particle velocity features, its directivity, being effective quantity, measuring in a near field, we can have like a very high signal to noise ratio. We can use that to more accurately identify, for example, noise location, and we can do that in any environment. So we have less susceptibility to the environment, to the background noises that may apply. Furthermore, as I mentioned, we can create like an acoustic multimeter. We can combine a pressure microphone with a velocity sensor, and this way we can also capture broadband sound intensity. So if we look at sound intensity, the principle behind it, it's relatively simple. It's like you take time average cross spectra between the sound pressure and the particle velocity. So since we can capture both pressure and velocity signal directly, we have a very straightforward way of measuring sound intensity. And because of that, we have no limitations in frequency. So we can measure broadband from 20 hertz to 10 kilohertz. We can make like a non-distributed small sensor that is actually doing a point measurement, which can be done for both one-dimensional as well as 3D dimensional intensity. But moreover, a big advantage is that it's also suitable to be used in high pressure over intensity environments. So this can be typically the case when you measure in a room or like a relative small closed cavity, like in vehicle interior, plane interior, whatever. So normal traditional sound intensity methods have difficulties with this parameter, and you always need to check it to ensure the quality of the data. But since we have the sensor that's not solely depending on sound pressure, but can capture both pressure and velocity directly, we can measure in those acoustic challenging environments. So the sound intensity can also be used for sound quantification by going to look at the sound power. So basically, what you can do is you can multiply the sound intensity with the area, and then you get the sound power. And sound power is like a very effective tool for all kinds of applications, like benchmarking products to get like analytic data. It's commonly used, as we say here, as a quantitative description of the acoustic output of a device, of a product, and what acoustic impact it has on its environment. And more you see this as well applied to consumer products, at least here in Europe. Like when I go to the shop to buy appliances, you can not only compare like, okay, the energy performance of a washing machine or a dishwasher, but you can also see the acoustic performance and compare them. So it's becoming more differentiating factor as well. So with our intensity probes, we have also a method, In-Situ method, to calculate fast and easy the sound power of products. So looking quickly at some sensors and solutions. Most commonly used sensors are seen here, that we also see later on in our solutions. So we have 1D and 3D probes. So in the so-called PEU probes, we combine one traditional sound pressure microphone with a microphone particle velocity sensor. So we just have different configurations to suit different applications. Just like a 1/2-inch regular, which is similar in size to a normal microphone. It can be easily mounted on a tripod or use handheld. The mini for array applications, to use multiple of them closely spaced. The match, which is really the smallest sensor of them all. The Voyager, which is designed as a robust probe to take outside the lab into the field. But all those probes, in essence, carry the same core technology, one direction particle velocity with a sound pressure mic. So we can use it for particle velocity measurements, sound intensity measurements, sound power measurements, absorption measurements. Since particle velocity is directional, as we mentioned, it has a direction. We can measure particle velocity in 3D. So we also have a so-called USP probe, which is a 3D sound intensity probe. So it comprises of 3 orthogonally placed particle velocity sensors in the X, Y, and Z, as well as a sound pressure microphone. So this way we can measure the 3D particle velocity as well as the 3D sound intensity, which can be very helpful as we see later on. So if we look at Microflown Solutions, there's like 3 main fields that we target. So we have unique tools that are being used for sound localization, as well as sound ranking, as well as material testing. So we have solutions like Scan and Paint 2D that help you to create very fast and easy a 2D sound map, just overlaying like a heat map for acoustics over an image. Then we move the whole application to 3D with Scan and Paint 3D, where we can get like 3D sound visualization over a 3D model. We can use array applications to localize transient noise or measure non-stationary conditions. A very intuitive way is also just listen and analyze. So put on the headphones, listen to the velocity signal, move around, and we use the power of our own brain to interpret what we hear to detect sound sources. Also, it can be related to more quantitative data. So the systems can be used for sound ranking. So it can be sound power ranking. So this can relate to any product where you can calculate the overall sound power, but you can also make like multiple segments with subsegments to see how much individual components or sections are contributing to the total sound power. So you can get like a sound power ranking table. In automotive, what becomes more and more important is not only just the total sound power, but relate them to specific orders. So this became especially increasing interest with the arrival of electric vehicles. We can do like a kind of airborne transfer path analysis, so-called panel noise contribution analysis. So you take in account 2 things. So in the end, you measure the contribution by measuring not only the source strengths, but also their transfer functions to a specific position. So, for example, if you have 2 sources with the same amplitude, like if one is closer to your ear, you will hear it more dominant than when it's far away. But if you have like a smaller, like one source with lower amplitude close to your ear, and a source with a higher amplitude that is further away from your ears, which one do you hear best? They have different source strength, different acoustic distance to your ears. So that's what we can measure here. So we don't focus like, okay, if you're a listener receiver, which are like the panels or the sources that are mostly contributing to what you hear. Also, what we can do is material testing. And to come back, in the beginning, we made like an analogy to electricity, like we have the voltage in amperes. If you want electricity, the power, you multiply voltage in amperes. If you want to get the impedance, you divide the voltage by the amperes. So basically here in acoustics, it was very similar. So as you saw on my slide before, if you want to get sound intensity, you multiply pressure and velocity. But if you want to get acoustic impedance, which you can use to calculate absorption, you divide the sound pressure by the particle velocity. So having a sensor that can measure both those quantities can be helpful to do in situ absorption measurements, as well as transmission loss, what we can do. So this is like the main field of solutions that we offer. So we can look shortly into some of them. So one is called the Voyager. We already saw it passing by in the video. So basically, Microflown started off as a sensor company, and one of the first things is like, okay, how you going to demonstrate people like what it is, particle velocity, and what is the benefit. So yeah, we tried to explain it. Yeah, you saw also my presentation animations. But what is better than really experience it? So we made like a small amplifier that could make the audio of particle velocity audible to our ears. So then we could just like, here, put on the headphones, listen. Okay, yeah, you can hear the directionality, the near field effect. But then also people said like, hey, this is also really useful for us as a product. Can we get it? And then we're like, okay, it wasn't just a demo. But then we made the scanner listen. So that's like one of the first products next to the sensors that we had. Slightly along the way, we start moving off becoming just a sensor company to being a solutions provider. So we created like some software, like data acquisition. If you want to use it portable, you need like a battery pack to power like the amplifier and dock. But as with many things, like technology innovation enables new opportunities, and what we already experienced, especially in the consumer market, where you see in like a small device, more functions are enabled and merged into one. So it's like the phone, like the iPhone. They were like even presenting it like that with the first iPhone. Like we had like an iPod, we had like a Safari on the computer to browse, we had like a phone to call, but now everything is into one. And that's basically what we've done as well. So basically all the individual devices that we used to have, we have nicely merged into a new product called the Voyager, which is a portable front end and analyzer. And it merges basically the things that we mentioned before into just one single device. So it's a portable measurement device with a built-in battery, so it can be used completely battery operated. It has internal storage memory to store the data. It has like the preamplifier, plus data acquisition built in. The nice thing, like Scan and Listen, we can connect headphones to it and listen to the signal in real time, but also allow us to do more targeted analysis enabled by real-time audio filtering. We can just go in the field, record data, analyze data. This all enabled by the embedded analysis software on the device that is very intuitive to use, fully touch control. Also similar to the phone, and bringing like this touchscreen experience, how we handle our smart devices, to also the measurement devices. It can be used like in different modes, just as a standalone device, but also as a portable front end for our PC-based software solutions. So, as mentioned, one really intuitive way of finding sources is just put on the headphones like this handsome guy here is doing, just connect the probe to the device and put the probe and listen what you hear. And in the meantime, you can do some spectral analysis as well, including like standard FFT, octave analysis. There's like a spectrogram option as well. There's some more advanced analysis in it as well, related to psychoacoustic parameters like loudness, for example. We can portably record data, later play it back or analyze it, apply filtering to it. So another nice feature here is like we can just use it as a standalone recorder, record data as we do here, save them on the device, and later go to the computer and like import the measurements done on with the Voyager into the computer, and then do some more thorough analysis. Like for example here, we divide like the several segments that we use. We can easily see here the sound power levels measured as a total, as well as for different sides of the device, and create like fast and easy a ranking, sound power ranking table, just in a matter of minutes in situ. So it can also be used as a network. So the Voyager can be remotely accessed with external devices like the computer or your smartphone, so you can monitor remotely, or also control the device, start-stop measurements. This way we can also easily remotely transfer data. So if we go here, put in like the network ID of the specific Voyager, like we're doing here, it will just show up as a network folder, and like we can download the projects that we have on the device to the computer for specific analysis. We make it also a universal tool, so you can use it to record data on the Voyager, store it. But what if you want to use it with other types of software? So there's like standard, it's safe also in an open file format called the HD5 format. But what we can do here is like also convert it to corrected, time corrected WAV files, either 16-bit or 32-bit, including dynamic range setting. So you can easily import it to other software platform for analysis. And in the NVH market, two really common one that we tested it and verified it with are, for example, Head Acoustics and MilliBBM PAC. So you can just record part with our sensor the data and later use them also in other parties for analysis. Also, people like to build their own software tools. So also we are interfacing. That will come later. So next to the standalone uses, it's like an interface to Phalo. Phalo is the name for our PC-based software applications. So the Voyager is like the new standard as portable front end. So it can be used next to a standalone device, also with the Phalo platform as a portable data acquisition. So we can use it, we can connect it two ways. One is like the classical way, just like connect by USB to the computer. But we also can use the network connection. So then we can use it as the acquisition as long as both the Voyager and computer are connected to the same network. So the nice thing that it enables is that it also can be in separate rooms. So if I would open other software, probably I could find some Voyagers here around the Microflown office that are connected to the network. So I could spy on them, connect, and hear what they're doing. But more practical, for example, here we put the Voyager in the test room, and we can connect with the computer to the Voyager to use it as a data acquisition from like a separate room, the control room. It's not limited to use as a data acquisition system for the Microflown Solutions, but we want to make it a more universal tool, more freedom to use it with your own developments or applications. So we also have a public GitHub for it. There's documentation and an API to integrate the Voyager DAC easily into your own applications. So a pretty versatile tool that can be used, as I said, as a standalone, but also as portable data acquisition system. So, okay, for what kind of application could you use it as portable data acquisition? So one really nice one to highlight is the Scan and Paint 2D. So the Scan and Paint 2D is like one of the first solutions that we introduced approximately 10 years ago into the market, and currently we have over 300 users worldwide. So Scan and Paint 2D is like an acoustic imaging tool that can visualize sound in this nice color map. It's like it looks like the weather forecast, where in the weather forecast red is like Texas, where it's warm, and blue can be like the Minnesota winter, where it can be really cold. But then for sound, so red is like a lot of sound, blue is like lower amplitude. The really nice feature here is that we can map sound broadband from 20 hertz up to 10 kilohertz. And because the way we can measure it with particle velocity, we have frequency independent spatial resolution. So we can get high spatial resolution in the full frequency range, and as well as a unmatched dynamic range of visualization. So since we don't need complex computational algorithm to reconstruct the sound field, we can like visualize over 40 dB, 40 dB dynamic range. Another really nice feature is that the same system can be applied on basically any product that makes noise. It can be like from small, medium to large devices. So we measured from a hearing aid to a car up to like a complete big gas installation. And within a very short time, we can create high-resolution sound maps for pressure, velocity, intensity. There's optional modules to combine it also to calculate transmission loss, absorption mapping, or air transfer functions to do contribution analysis. Also, since we have a pressure velocity probe that we use in the application, we can get the sound intensity, we can define an area, and get sound power calculated. So it's a very easy system. We use the data acquisition. Here we see like the traditional one. It can be the Voyager nowadays with a probe, a camera, and a computer. So how do we measure? So basically, we swipe with a pure regular probe over the surface of interest to capture the data. And what we can do is with specific color markers, as you can see on the right side, we can follow optically exactly the position of the sensor over time. So we create like a nice trajectory over time, and like by breaking the continuously time cycle into small pieces linked to the position that we track, we can obtain very fast and easy sound map. Just to make it clear, we swipe, you see on the right side, it follows optically the position, and we can get a high spatial resolution color map as a result. So one example here that we applied, one of the first measurements actually done here in our office, like related to building acoustics. We put like a speaker outside the room, an omnidirectional sound source, and we scan like the surface moving with the probe over the door, window, the wardrobe. And what you can see here is like broadband particle velocity color map. So you can see, as expectedly, most dominant is like leakage around the door, in this case like the floor and a little bit at the top. But what we can do is also select specific areas and plot like the average spectra for that area, or like map at specific frequencies. So if you go really low in frequencies, for example here, what you can see at 87 hertz, you can also see this peak as highest in the, which is the green line over here. You can see that there's like a mode in the window. If we look at some other frequencies, we can see, strong leakage. Oh, spring is coming, so hay fever joins it as well. All right, back to the slide. So you can clearly see the leakage. And here with the wardrobe, you could see it was like an empty wardrobe in this case. You get like a cavity resonance based on the size of the cavity that was actually booming at the 265 hertz. So a nice practical industrial example, in this case, done for Rolls-Royce. So there was like a station in Europe where there was like a huge gas compressor. So basically, gas is pumped from the Black Sea into Europe by this infrastructure. And in this case, two parties were like arguing who was like the cause of the noise. So one company was responsible for the gas compressor, that was Rolls-Royce. Another company was responsible for the piping infrastructure. And in this case, when you entered this facility, you directly wanted to go out. It was like insane noise level. And the peak measured was like 115 dB. As we saw later in the measurements, also it was a harmonic peak, the issue for the harmonic peak at just above 1 kilohertz. So it was a pretty annoying noise to perceive as well by a human. So they applied here the scan and paint 2D to find out who was right, Rolls-Royce or the other company. So this was done in just like just over half an hour to 1 hour work. So we scanned like, we did 3 scans, like the discharge side of the compressor and the piping, the compressor itself, as well as the suction pipe. So in the end, even if you have like this large structure, you see you have like a pretty reverberant environment with a lot of reflecting surfaces. In a short matter of time, we could like directly pinpoint to the dominant source, which was in this case the strainer in the middle of the suction pipe. So this is like a special filtering system to avoid that like other pieces than the wanted gas or entering the compressor and could possibly damage the compressor. And so we could pinpoint the strainer was like the problem that had like some resonance problem in the way they designed like this kind of metal mesh inside to act as a filler. And after they found out this problematic part, they could look into it and create over 10 dB reduction by replacing this faulty strainer. And the people that were in the factory were really happy with that, as well as Rolls-Royce, because they hired us to do the measurement and could prove that they were not to blame. An example related to automotive, this was like a case done with Bentley. So they wanted to optimize their body in white. So this is like the naked frame of the car. So when people are designing the car, they are not considering acoustics. It's just purely aesthetic. Design a nice looking, sporty, luxury car. But like the way the body in white is designed, it can imply that mode shapes appear into the structure, especially structure-borne problems could occur when there is like an engine running, or when you drive on the road, like the tire-induced resonance that can go into the structure. So in this case, typically what they do, if you have the body in white, they apply special packages of damping material to the structure to reduce already in an early stage structure-borne problems that could later cause into noise perceived by the driver. So actually, Bentley is part of the Volkswagen Group, and they're based in the UK, but they're pretty smart. Like they buy in the main technology or the platform from Porsche. It's based on the Porsche Panamera. But yeah, who would trust the Germans? Well, they don't. So they thought like, okay, we can do it better. So they bought it originally in with already the patches mounted by Porsche on the body in white, and they wanted to see if we could, in a short time, optimize the acoustic treatment package. And especially here, it's like getting more and more important due to also the emission regulations to reduce weight. Like there's several ways to reduce emissions, and one is like, okay, the less weight you have to move, like the more efficient you can be. So what they wanted to do here was like optimize the damping patches applied to the body in white, reduce the weight, reduce the cost of the treatment as well. So just as an example, what you can see here is like the average spectra of a measurement. One panel as example, the floor here, and you can see the undamped and the damped. So in red we see the undamped, where we see clearly 3 high peaks. And we can see below, even being relatively low frequencies, we can clearly get like a high spatial resolution mapping. So we can see like the mode occurring there at 175 Hertz, then 270 and 430 at different locations. Just to give you also an idea, we cannot show the exact amplitude, but the dynamic range of visualization. So then the difference between blue and red is 25 dB. So based on that information that they can obtain with the system, in this case, they could design a much more effective panel treatment. So they could see where they could remove patches that were not effective, or where they could improve by putting extra material. In the end, the outcome was that based on these measurements, they could reduce the panels by 15%, which also is like a cost reduction of 15% per produced car. And a nice additional feature that they gained as well is that also the acoustic performance was better. So after they took like the baseline car on the road, measure the overall level, compare it to the modified car, and like in the overall band, we gained like 1.3 dB in acoustic performance as well. So in the end, like very good outcome, achieve better acoustic performance while applying less materials, reducing the weight and cost. So the full application cases and papers can also be found on our website by the link, so you can look more into it. So these are nice 2D color maps, but yeah, 2D is just 2D. What we can do in 2D, we can also do in 3D. So with Scan and Paint 3D, we can measure 3D sound factors on a 3D model. So instead of just having this 2D image overlap on the 2D image, here we can get much more out of the results. So we can see, for example, here is the speaker, not only where is the origin of the sound, where is the source, but also how does it propagate away from the structure. And in one visualization, we can go all around it and see how sound is going all around the object. It works in essence very similar key features. Like we can measure the full range, small, medium, large devices. We can get like a high spatial resolution mapping, in this case down to 3 millimeters. We can visualize sound pressure, 3D particle velocity, 3D sound intensity. We have like automatic 3D tracking of the position. And also, based on the sound intensity data, we can calculate sound power. Looks a bit similar. A normal camera has been exchanged for a stereo infrared camera with like a sphere with reflective markers to automatically track position and orientation. In this case, we're not using just a one-dimensional probe, but a three-dimensional probe, which is like a big difference. So this is the sensor that we use here that consists actually about 4 sensors, 1 pressure mic, 3 orthogonally placed microflown sensors. So we can measure in 3 directions sound intensity, and by taking the modulus, we can get like the amplitude and direction visualized into a sound factor. So how does it work with Scan and Paint? 3D, we can measure all around, in this case, the head. So what we first do is create a 3D model. We can load one if we have, but we also have a tool, as you can see here, to scan and get quickly a 3D model. We use like an automatic tracking system based on a stereo infrared camera combined with a sphere with ER markers with a unique pattern that can track in real time the position and orientation. We can scan around an object, and there's like automatic link between the real object and the 3D model, and we can easily visualize, in this case, the sound diffraction around the human head, and nicely see not only amplitude but also direction of the sound based on particle velocity, sound pressure, or sound intensity. So it can be vector field, sound pressure, which is in this case bulbs because it doesn't have direction, but also we can create like areas and interpolate the data into 2D sound mapping, which in some cases can give you a more clearer picture of what's going on. Another nice feature is the sound power calculation, the total or also divided by area. As we mentioned, we have sound intensity data, we have a 3D model with dimensions, So combining that, we can get the sound power. So the nice thing with one set of measurement data, you can do both the sound power calculation and ranking, as well as the sound source low position and ranking. So one concrete example here where it has been applied. So in this case was like you can see here the steers on the right side, which is for us not the right side, but in the UK it is. This was a Jaguar car. What they did here was use it for audio system verification. So in this car there was like a new audio system installed, and they want to characterize the audio sweet spot and verify the audio systems of several equal vehicles. So they needed like to get high spatial resolution mapping, in this case in a complex acoustic environment. And what they wanted to check here is like how inside the car the sound goes. Sounds a bit strange, from the driver to the driver. In this case, one driver is the speaker, the other driver the listener. So how does sound behave inside the vehicle? So we can see here on the top two pictures that if you look at the low frequencies, you could see like the speaker, the driver installed in the door panel, and the sound is like it has like homogeneous distribution to the position. You can see at other frequencies, higher frequencies, there was like a tweeter installed in the A pillar. But what we've seen and measured here in this vehicle that was interesting is like where's like problematic frequencies and areas occurring. So in this case, you could see here like there was like a strong cavity resonance, like a strong note where you get like a large delta in amplitude on two close points. So in this case, this cavity resonance at this frequency was resulting in over 10 dB differential between the left and right ear of the driver. So that's perceived as pretty unpleasant. So they could directly see, okay, what can we change on the acoustic properties or on the driver's type of driver location to get rid of the cavity resonance. As well as here for squeak and rattle identification. So in this case, they put like a low pass signal source through the car audio system, and this way it excites structure, and you could use that to find locations where panels could get like rattling. So in this case, you could identify the plastic cover that was not well mounted and designed in this car close to like the door panel as well, the window and mirror attachment. And the nice thing is, like with the sound factors having the direction, you could see if it is really a problem or not. So what you can see here is like clearly the source is identified, and you can see that all the sound factors are coming from one position, propagating away into the area, in this case the vehicle interior. It can also be nice to target more complex problems. In this case, it was like in the cabin of an airplane. In this case, was related to the ECS or the HVAC, the climate system. There's like big systems that are under the floor. So they were expecting like, if there's problems, there's probably related to the floor, where directly the floor acts as a how you say it, as a loudspeaker, like when there's some structure-borne issue. We could see, as we see in the pictures, the results below here, that we did find some location where there was like this issue, especially with like the mounting of the seats to the floor, that you get the excitation. But the main issues were related to how sound goes through the piping, and especially here at the top you see like the flutes left and right. So this is like kind of T connection where the flow is forced to go left and right. And the complex thing here in the end is, with most systems, you can see sound relatively easily where it comes from if sound radiates perpendicular away from the surface. But in this case, there was not a case. As I said, you had this T connection, and what happened is that it was the sound field was much more complex. So initially, sound was radiating under an angle from the surface and then bent it down towards the perpendicular to the surface, towards the passengers sitting at the seat. And this was also in an annoying frequency range as well, like 2 kilohertz, 2-3 kilohertz, and pretty dominant there. So what you could see is like with these 3D visualization, you could see, okay, it originates from this T-flute, it moves and then bends down into the cabin. But also there was like some different areas as well at different frequencies. This is like a broadband visualization where sound came in, leaking from the ceiling grills as well as the extraction grills that are like close to the floor on the sides. So this gave them complete new insight where actually the sound was coming from. So this is just some example how we visualize sound with the 2D and 3D. The last topic that I will touch in today's webinar briefly is another application. So one way to attenuate sound is by applying damping, absorb sound. So what we have also is like an in-situ absorption system. So we can use the software with a data acquisition, and we use like we call it the impedance gun. So like a speaker combined with the PU probe. So we can point it towards the material and use the acoustic impedance, dividing the pressure and velocity to get acoustic impedance, you get the acoustic absorption. So this way we can fast and easy in situ test samples or completely assembled units to get, like in a matter of minutes, the absorption curve. The nice thing, if we combine it with a type of scan and paint way of measuring, so scanning the surface with the absorption gun, we can also get like a special representation of the material properties, which is especially interesting if you design like resonators or like porous materials, non-homogeneous materials. But like I said, the nice thing is also like you can test complete, not only samples, but complete manufactured products. In this case, we tested car seats, and this like Volkswagen Golf was supposed to be exactly the same seats. We went like to do the measurements in situ, as you can see in the picture, to prove like the repeatability of the measurement system itself. We measured like, we used one car as a reference that we measured many times. So on the left side, you can see if we measure 24 times the same car, you get like almost every time the same result. There's hardly any deviation. But when we measure 24 times the different car seats, you can see, okay, the same materials have been applied, but there can be still quite some variation overall, between the different seeds that's supposed to be having the same absorbing properties. So that was it, the main content for today. In the future, we can go specific more on solution level, go deeper in the different systems we offer. But today I want to mainly focus giving you a quick introduction. What is a microphone sensor, what it can do, where it can be applied to. So from my side, I would like to already thank you for your attention, and I think we can move on to the final part, the question and answers.
Right. Really great information, Jeroen. Appreciate it. That really gives you a complete look at everything Microflown can do for you. I think it's pretty amazing technology. Looking at the attendance list, so if anybody has any questions at the moment, I think we're a little in over probably an hour and 15. If you have any questions, you can reach me at kent.peterson, Peterson, at Microflown, I'm sorry, at warkwyn.com, warkwyn.com. Of course, you can also reach out at Jeroen at either info at warkwyn.com or info at Microflown. Is that right, Jeroen?
Yeah, sure. I mean, they can use you as main point of contact.
Right. We do have systems in the U.S. We've got a system in Minneapolis that we can demo for you, or have you with a more personal webinar and show you how the product can help in your needs. Of course, we focus on speakers, so it's very interesting for us to see how in the 3D and even in the 2D field how sound impedance might wrap around and diffract around a speaker. It's very helpful us in visualization. First time I use a system, I brought it to a tractor company in North Dakota, CNHI, and I wasn't very familiar with the system at all. And I set up a demonstration on an in-situ motor on a huge tractor. And we were able to find the problem within 45 minutes, something that they've been trying to sound localize for about 6 weeks. That company wound up purchasing a complete system. So outside of me babbling anymore, thank you guys for showing up. I appreciate it. I don't see any questions. Thank you again, Jeroen, for your time. I think it's beer time for you in the Netherlands, right?
Yeah, almost. Yeah, dinner after pop up a beer.
Netherlands makes good beer. I like it
Sounds
myself.
good. My working day is over, so you still have the day ahead. So yeah, once more, thank again for joining, and yeah, don't be a stranger. Feel free to drop questions, ask for a demo, and thanks again.
Sounds good. Thanks, Jeroen. We'll talk to you soon. Everybody have a good evening, morning, whatever. Hope to hear from you soon. Thank you.